Can you hear me in the back? I can barely see you, but I'm sure you can see me well. So realizing that you've been sitting there all morning, I'm going to seek your participation in here as well. It will not be just me standing here and giving you Intel's perspective in the exciting world of VR, but I want to hear your perspective as well. So first of all, I hope you all agree that we are in a very exciting phase for VR, AR, and MR. Today, the short time that I have, I'm going to focus very much on the virtual reality world, and I'll show you how the real and the virtual worlds are merging together. All of the speakers before me have done a fabulous job in explaining the same story. And for those of us that have been in the computing industry, in information processing, sensing technologies, computer vision, graphics, and display technologies, this is a very exciting time because all of that are coming together in making something possible that were limited to science fiction. Finally, things are coming together to the point where we can start to scratch that fiction from science fiction. How many of you consider yourselves as hardware engineers here? Can I see a hand? Quite a few of you. How about software engineers? OK, a lot more. How about systems engineers? And then we get to the strange parts. How about human factor engineers? We're interested in human factors. How about storytelling, applications, marketing, business? And we all have to benefit from this era of virtual reality. So let me just get quickly started. I don't have time, given the short time, to go through the definitions, but you pretty much I think we have a convergence of opinions that VR is where you have a head-mounted display that occludes your view of the natural world so far. And then augmented reality is where you pretty much see through either your transparent display on your head or on your mobile device through a camera, and then you overlay digital content into the real world. And we now have the new category of mixed and merged realities. And I'm going to share with you our views of that. But I think as it goes to the definitions, we might as well just start by defining reality. So what is real? How many of you have watched the movie Matrix? For the rest of you, I have to say you must watch it. So Morpheus asks the question, what is real? And he repeats himself. How do you define real? And he goes on to answering himself. If you're talking about what you can feel, smell, taste, and see, then real is simply the electrical signals that are interpreted by your brain. Looking back, I think there was a profound definition of real. It's an engineer's view of reality. Because if you can define reality in terms of the engineering terms, I think we then can get to work and build it with technology. And it's just reflect on it for a while. You know, I'm looking at you all sitting here in the room. To me, you are simply what, mostly the visual sensation my eyes and visual cortex combination are creating. It's the lights that are being created here in the light sources reflecting on your face and the chairs and the room. And I am constantly reconstructing the wall. So to me, you're simply reconstructed people. So those are simply electrical signals that are zipping around in my cerebral cortex. That's, to me, who you are. And same in your day-to-day interactions, what you smell, what you taste. This is all simply what your brain is reconstructing. So we should be able to then break that down into sensors, computing technologies, and rendering and display technologies to be able to get to fooling your senses into thinking where you are versus where you're not. And that's the goal for the VR and AR engineers. We have the definition behind us. Now let me get to virtual reality, because that's what I'm going to focus on for the rest of the talk. Again, from the viewpoint of a company like Intel, who have pioneered the microprocessor largely for its entire existence, it's a very exciting time of how the computing technology itself is evolving. Let me just take a quick light question here. How many of you have played with the Intel 4004, the first commercial microprocessor that Intel shipped in 1971, way before some of us were born? Can I see a hand? Anyone tried 4004 machines? How many transistors did it have? You know, the worst thing you can do is make a mistake in front of the room full of people. But don't let that hold you back from answering. How many transistors did Intel 4004 have? 4004. Close to it. Actually, it's 2,300. And how many do we have now in your state-of-the-art laptop, whether it's a MacBook or Microsoft Surface Pro or a whole bunch of other laptops? Billions. So in 45-something years, we have packed in more than 1 million times more transistors, 6 orders of magnitude higher. That's just the computing technology. You have enormous progress in sensing technologies, being able to miniaturize computer vision sensors to capture the world in 3D, in very small, tiny form factor that you could embed in your headset. And display technologies, you know, from the early XGA monitors to having 4K by 4K pixel resolution in tiny displays in your headset. It's amazing. So if you look at from the sensor technologies to computing and graphics technologies to the display technologies, you can imagine why all of us are here and excited about VR and AR. Obviously, as you look at the computers, things got smaller and smaller. We all have our phones with us, but we give up something, right? We give up the large displays we like to enjoy in our workstation or in the office or at home. VR totally unleashes the visual experiences. Suddenly, you have this entire world as your visual field. That's quite amazing in technology. So we're pretty excited about this. I don't have to tell you what all applications it can enable. No, VR is not just about games. We already have compelling applications that are going beyond just games or watching a movie on a virtual large screen. You're already able to transport yourself from your living room into a vantage point in a stadium to experience the game as they're being played, or in a theater enjoying a musical performance. Imagine in classrooms where you teach the students about a three-dimensional DNA molecule that's rendered right in front of the room, or the solar system, whole bunch of applications. We have barely started scratching it. But that said, we have challenges and a lot of work for those of us that are engineers. Hardware, software, systems, applications, and some of them I'm going to call out today. Freedom of movement. For some of the applications, you do need the strong, powerful microprocessor and the best of graphics cards that you can throw at it. So there is legitimate devices that will need to be connected to a very powerful PC. On the other hand, you will also need fully untethered, cordless experience where you want to go around in your large space, not being burdened by a cord that connects you to the devices. You need natural interactions. Those controllers are amazing for fine control of content on the screen. But for most interactions, we humans have been interacting with our hands. There are a whole bunch of neurons that are dedicated to understanding how you touch with your fingers. And you need natural interactions like that, even with the virtual world. We want to blur the real and the virtual. I'm showing you here a picture where real hands are moving virtual chess pieces. And there are a whole bunch of other things that you can think of. That needs to be done. Finally, seamless experiences. This is not just where the sensors and computer technologies will do the trick, but you need displays that are amazing, that are going to be lifelike. And I'll tell you about our view of how many pixels might be sufficient or needed for seamless experiences. So with that, let me just do a quick highlight of what Intel contributes here for the VR ecosystem. Obviously, we're very proud of our core microprocessors. We just announced our 7th generation core microprocessors for awesome laptops and same processors that are powering, along with its integrated graphics. Amazing power and packed into a small form factor to power VR and AR experiences, whether it is VR headsets connected to your laptop or desktop, or VR headsets that are all-in-one. I'll talk about that. On the right, you have the data centers. Why do you need that? Well, some of the previous speakers have already explained that if you're going to capture the world in real time in 3 dimensions, and remember, I need to create electrical signals in my brain that creates the sensation of being here, even if I'm not here. That means capturing the millions and billions of points as 3D point cloud and reconstructing the world. So some of that work you will need to do in a very powerful data center. So we're very proud about the Xeon processors and exciting line of technologies we have for machine learning in that area. But in the middle, we have been working really hard for the last few years in extending Intel's technologies to bring technologies like Intel RealSense for real-time 3D visual sensing system into all kinds of devices. You might have seen our work on Movidius to develop and bring to market low power and power efficient vision processing unit to run computer vision algorithms and machine learning classification right on the device. We have WiGig. You've seen our announcement with HTC that will be working together to uncord even powerful VR systems from the PCs. We have Thunderbolt to simplify the wiring between devices, and also breakthrough memory technologies like Intel Optane, so you can load your applications in light speed. So with that, I want to explain to you out of this the wide spectrum of work that we have at Intel, along with our partners. There's no one company that can do it all. This is truly an area where it's amazing to see all of the companies, whether they're established companies like Intel or a bunch of very exciting startup companies, really coming together to make this happen. And so I'm going to focus on one aspect of it, which is how far are we towards this fascinating world of merging the real and the virtual. We have showed off Project Alloy at CES. So Project Alloy for us is an experimental headset where we push the envelopes off, completely untethered. We put in our best processor inside, that's PC class processor and graphics in there. We put in integrated inside-out 6-DoF tracking, so you don't have to be encumbered by external tracking systems for mobility. Natural manipulation, and you should be able to see your own hand in the VR environment. And also bringing in the real world into the virtual world. So that's Project Alloy. Let me show you just what's under the hood. So to build this device, grounds up, as I said, we put in Intel Core processor inside, Intel RealSense depth sensing technologies, 6 degrees of freedom tracking sensors, extremely important for lifelike interaction in the virtual world. 3 rotational degrees of freedom and 3 translational degrees of freedom, so that you can get close to virtual objects and have a 6 degrees of freedom experience, quite important. And obviously, we have Movidius vision processing unit for lowering the power and accelerating computer vision algorithms. So given the short time, I didn't have a chance to bring demos here, but I don't know how many of you got a chance to see the demos of Project Alloy at CES. We also have it in the exposition. Please go and enjoy it. But I did bring a small clip to show you what Project Alloy can do. And it is a recorded demo, so please enjoy.
Now, the first thing I want you to notice, there's no sensors in that room. Those of you who have played VR before, you typically either have laser sensors in the corner or tracking cameras just like you have in tables in front of you. But with Project Alloy, we have seamless tracking built right into the headset. So no needed extra hardware. Now, also, take a look, no cables attached to them. So playing this completely untethered, they're able to move around the room freely, not tied to their computer. Now, we've already scanned the living room. You can see it on the computer, on the screen above us. So Eli and Jan, can you start the game? And we're going to convert this living room into something a little bit more, I don't know, entertaining. So now you're going to see the sofas, the chairs, the bookcases. Those are all going to go away. We're going to get radar. We're going to get armor bunkers. We're going to get shield generators. We're going to get plasma power supplies. All that comes into the living room, making our gaming experience much more immersive. Who wants to shoot over their couch, right? So pretty soon you're going to see the walls, which were walls, those go away. Now we have a great sky view. Now we're truly in a gaming environment that took us completely out of our living room.
So now this is a gaming environment that is typical of what I'm used to.
Exactly. This is a great gaming environment, and they're able to play. Pretty soon you're going to see the spaceships coming here. They're going to shoot them down. But notice they're able to still walk around the living room. They're able to hide behind the couch, which is no longer a couch. It's now a bunker. We're able to shoot the aliens or the spaceships, and yet we have this great gaming experience in our living room, but still the room becomes part of our gaming experience.
Okay, so hopefully you got a good sense of what a merged reality device can do. Please enjoy the demo at exposition. That was Intel CEO at CES. So I also want to show you one little other demo, and that is enabling natural interaction with digital content with your hand in VR. So VR, as you know, occludes your view of the world. But with RealSense technologies, we're able to bring in your real hand. This is not an articulated hand, but your real hand, because we have a depth sensor in there, along with high-definition color images, so you can reproject the color picture onto the point cloud and give you your real hand. So you have what psychologists call the correct proprioception cues, so you don't get nervous. And it's quite freeing, so I want you to see this demo. So you can see it's a metal lathe, obviously virtual, and you are playing with it with your real hand or any other object that you might have, a real-world object. And when you play with virtual content with your real hand, it feels magical, because suddenly you feel like it's part of the real world. It's not just a virtually rendered world. It's a perfect example of a merger between the real world experience and the virtual experience. So the couple of minutes I have, I think that we all sort of feel like we are on this verge of something exciting about to happen. Yet, virtual reality has been there before, where it didn't live up to its promises decades ago. Yes, technologies are getting to a point where you can already experience mainstream applications in VR, but there's a lot of work for us to do. I didn't have time to lay out all the technical details, but I want to summarize a few things that collectively we have to. You have to reduce latencies, everybody knows that. And the number that goes around in the industry is you need to be from the onset of detection of your motion to the last pixel of the screen emitting light into your eye, the motion to photon latency. Typical numbers being quoted today is 20 milliseconds. We're almost there, but I can guarantee it will not be good enough. So we have work to do between the sensor technologies, the processor graphics technologies, and display technologies to reduce the overall latency from the movement to the photon. When I move and I look here, I see you immediately. It would be actually pretty disturbing if I still see the other person when I looked at you. It'll part of the reason it makes you sick. And we think that now we're starting to understand really in details of the visual vestibular mismatch that cause some of the severe motion sickness. So it's not just the technologies. While we are still figuring out how to reduce those latencies, the content generators have to keep in mind. Please don't let me fly over San Francisco fast when I'm just sitting on my chair, because that's going to create visual vestibular mismatch that no technology can fix. Other areas, obviously we are hard at work between processing and graphics technologies to render as many triangles as we can to give you rich visual experience. How about the displays? We'll need to create high-resolution displays. Well, displays are already high resolution, aren't they? The smartphones of today, they have almost 600 ppi. That's amazing, because for that viewing distance in a small screen, a little over 300 pixels per inch is probably good enough. You have close to 600 pixels per inch. But here's what happens. When you put such a display on your eye and they have lenses and magnifying it 30x, ppi is no longer good enough definition. Now you look at pixels per degree, like how many pixels you have in a degree of visual angle. And the number looks pretty shabby. Even a close to 600 ppi display drops down to less than 30 ppd. The visual acuity is 60 ppd. So we're at least a factor of 2 behind. So we've got work to do. And by the way, don't just let the display engineers sweat and pack more pixels. I think we can help from the viewpoint of graphics and optics, how to reduce the screen door effects. A lot of exciting work going on, tapping into diffraction techniques to reduce the pixelations and all that. And we are just about on the cusp of all of that work that we think are feasible to be solved. And then you will unleash a really awesome VR experience where every one of us will want to have one. And I'm looking forward to working with each one of you in seeing that future happen. Thank you very much.